faithfully conveying value and interpreting great books from around the world. Hello, this is Sally's Book Club. Today we're exploring the book, What is Physics? Physics undoubtedly forms the backbone of modern civilization. The smartphone before you, the AC in your room, the skyscrapers around us all exist thanks to physics. It's hard to imagine what primitive society we'd inhabit without physics. So, how did this discipline emerge and develop? What is physics? This book answers that question. You'll discover how the legendary Mercury retrograde influenced scientific progress. What principles underlie the heat death theory predicting cosmic fate? How do scientists use statistics to study microscopic molecular motion? What relationship exists between science and technology? Before diving into the book, let's meet its author. Japanese physicist Shinichiro Tominaga loved tinkering with magic lanterns and magnifying glasses since childhood. In 1926, he entered Kyoto Imperial University's physics department, now known as Kyoto University. Later, through introduction by Yoshio Nishina, father of Japanese physics, he studied in Germany. 2 years later, WWE erupted and he returned to Japan. Amid militarists diverting research funds to weapons, Tominaga persevered through hardships, later rebuilding post-war scientific institutions. In 1965, Tominaga shared the Nobel Prize in Physics with Schringer and Feynman for quantum electrodynamics work. During retirement, he delivered public science lectures across Japan for a decade, forming the basis for What is Physics. Tominaga passed away from laryngeal cancer in 1979, leaving this work tragically unfinished. The completed manuscript was published by Iwanami Shoten that year, winning the 1980 Asaha Prize. Continuously reprinted 58 times since 1979, this book remains a Japanese bestseller, a true phenomenon. So what exactly is physics? Tominaga offers a concise definition in the prologue: the discipline of seeking natural laws through observable facts governing phenomena in our world. Empirical observation forms the cornerstone of physics. How did this defining characteristic gradually take shape? What exactly are these natural laws we strive so hard to uncover? And in what forms should we articulate them? Let's journey through time with this book to explore physics' essence via classical mechanics, thermodynamics, and kinetic theory development. Part 1 brings us to classical physics. Humanity's cosmic inquiry began by stargazing. Ancient observers noticed celestial bodies followed strict schedules. Earthing astronomy. Early astronomy blended with astrology's mystical practices. Scholars proposed various theories about celestial movements. Around 2nd century AD, Ptolemy proposed his geocentric model. He claimed Earth was the universe's center with orbiting celestial bodies. But Mercury retrograde, apparent backward motion, puzzled observers. All planets exhibit retrograde motion. How to explain this? Ptolemy's solution. Complex combinations of circular motions made his model unwieldy. The geocentric model sufficed with primitive observation tools. Improved technology exposed calculation inaccuracies in planetary orbits. 16th century Copernicus revolutionized astronomy with heliocentric theory. Mercury's retrograde illusion stems from Earth and Mercury orbiting Sun at different speeds. Copernicus insisted on perfect circular orbits, conflicting with observed speed variations. Early 17th century saw Johannes Kepler's astronomical breakthrough. Using Tycho Brahe's precise data, Kepler discovered 8-minute error in Mars's orbital calculations. Some might think this is no big deal, but Kepler's OCD couldn't tolerate even an 8-minute error. Kepler wondered, could the problem lie in assuming perfectly circular orbits? This suspicion might make ancient Greek scholars turn in their graves, but Kepler boldly proposed that blind faith in circular motion had obscured planetary truths for centuries. Using Mars's opposition alignment, Sun-Earth-Mars straight line, Kepler geometrically calculated its orbit. The result? Mars's orbit wasn't circular, it was elliptical. Not just Mars, Earth and all planets follow elliptical paths. This became the essence of Kepler's first and second laws. A decade later, Kepler discovered proportional relationships between orbital size and revolution period. This third law, what exactly does it state? It reveals all planets follow identical mathematical patterns of astonishing simplicity. Naturally, we ask, what mysterious force governs these celestial motions? Kepler suspected solar influence but couldn't identify the exact force. Today, even children know this force is gravity. Of course, Newton would later provide the full answer. Now let's turn to another pioneer from Kepler's era. Galileo's legendary Leaning Tower of Pisa experiment remains iconic. He supposedly proved different weights fall at same acceleration through this demonstration. While the tower story may be apocryphal, Galileo's experimental rigor is undisputed. He meticulously documented all his experiments. For instance, timing balls rolling down inclined planes revealed uniform acceleration. By modern standards, Galileo's experiments seem elementary, yet remarkably, pre-Galilean scholars believed pure reasoning alone could unveil truths. Thus, with Galileo, physics truly became grounded in empirical observation. Beyond experimentation, Galileo emphasized mathematical reasoning. He viewed natural laws as an interconnected mathematical system. By establishing fundamental axioms through mathematics, we could derive numerous laws without endless experimentation. Galileo famously declared, "The book of nature is written in mathematics." He believed mathematical literacy was essential for deciphering nature's secrets. Therefore, physics required both experimentation and mathematical proof. Kepler and Galileo pioneered new frontiers. Now Newton would build their foundation. Galileo's falling objects demonstrated uniform acceleration with continuous velocity change. How could infinitesimal distances in fleeting moments sum to measurable quantities? Modern math students recognize this as calculus. But calculus, developed later by Newton and Leibniz, solved these very problems. Newton mathematically defined relationships between displacement, velocity, and acceleration. This milestone proved no suitable math? Invent new tools! Newton's crowning achievement: three laws of motion, governing force, inertia, and motion. Declarified that forces alter motion. Objects maintain velocity without external forces. Why are these laws revolutionary? Pre-Newtonian thought separated celestial and earthly mechanics. Newton unified all motion. Stars and stones obey identical laws. From these axioms, we can predict motions from cars to rockets. Galileo's vision of physics as mathematical deduction from fundamental axioms found perfect realization in Newton's work. Newton synthesized Galileo's experiments with Kepler's observations, establishing physics' empirical foundation. Thus, physics shed its mystical past, emerging as true science distinct from astrology and natural philosophy. The science-technology relationship makes fascinating study. Ask people about their difference, most confuse them as identical. Science explains why the world works. Technology changes how it works. Understanding nature's laws makes technological innovation more precise. That trial and error can also drive technological progress without scientific basis. Technology doesn't always follow science's lead. Like the Dutch telescope invented in 17th century. Optical science was primitive when telescopes emerged. Mechanical water pumps preceded understanding of atmospheric pressure. Telescopes enabled precise celestial observations, crucial for Kepler and Newton. Newton's optical studies stemmed from telescope research. Pascal's atmospheric pressure studies explained water pump limitations. These cases show technology often precedes and drives scientific discovery. Part 2 examines thermodynamics through steam engine development. James Watt's 18th century steam engine improvements powered the Industrial Revolution. The childhood kettle legend oversimplifies Watt's systematic experimentation. With harnessing heat energy for mechanical work proved revolutionary. Such heat-powered devices are called heat engines. Though steam engines are obsolete, modern life still relies on heat engines. like car and aircraft engines. Car owners want fuel efficiency and power, requiring optimized heat engine performance. Watt established research facilities specifically for improving steam engine efficiency. French engineer Carnot criticized Watt's trial and error approach as unscientific. Newtonian physics quantified water wheel efficiency through water volume and height. But heat engines lacked such fundamental principles. Carnot sought their Newtonian laws. This exemplifies technology driving scientific inquiry into basic laws. Carnot conceived an ideal heat engine using air cycles between hot and cold reservoirs. Air expansion or contraction drives piston movement during heat exchange. Carnot proved this frictionless process achieves maximum theoretical efficiency. Maximum efficiency depends solely on temperature difference between reservoirs. This raises fundamental questions. What exactly is heat? What defines temperature? Why must heat engines require both hot and cold sources? Carnot's early death, 36, left these questions unanswered. Joule's experiments established heat's mechanical equivalent, confirming its energy nature. Recalling Galileo's vision, physics as mathematical system derived from axioms, Newton established this framework for classical physics. Though brilliant, Carnot's thermodynamics lacked mathematical formalism initially. How do we derive other laws then? German physicist Clausius completed Carnot's unfinished mathematical work. He mathematically explained why heat engines require both hot and cold reservoirs. Understanding temperature differences' significance is crucial here. Clausius proposed temperature difference indicates system imbalance, enabling energy flow and work, like water flows due to elevation differences. A balanced system resembles still lake water. No changes occur, thus no work can be performed. Clausius named this imbalance measurement entropy. Lower entropy means more usable energy. Higher entropy indicates equilibrium with less available work. His entropy increase principal states. Isolated systems entropy always grows. Entropy became fundamental across disciplines, even predicting cosmic fate. Clausius declared, universal energy remains constant. Entropy trends toward maximum. This leads to heat death hypothesis, universe becoming motionless at maximum entropy. Though foundational, thermodynamics' macroscopic scale posed limitations. It described bulk properties, temperature, entropy, seemingly unrelated to Newtonian mechanics. How does thermal energy relate to mechanical energy? This remained unclear initially. Galileo's wisdom echoed natural laws form interconnected system. Thus, thermodynamics and classical mechanics must fundamentally connect. How then can we bridge thermodynamics with classical mechanics? Scientists speculated. Microscopically distinct phenomena might share microscopic foundations, like two garments differing completely in size and color to both be cotton textiles at microscopic level. Microscopic perspective offered promising breakthrough. Early 19th century understanding of microscopic world remained primitive. Chemists' atomic theory proposed molecules as chemical reaction units. And intriguing physicists, if molecular motions followed Newtonian laws, perhaps thermodynamic laws could be derived. Could this unify classical mechanics with thermodynamics? Excitement grew as physicists sought molecular macroscopic relationships. Gas pressure became investigation focus. Known PVT relationships lacked fundamental explanation. Clausius proposed pressure results from molecular collisions with container walls. He formulated pressure as collective molecular kinetic energy. But why does temperature affect pressure? Boltzmann revealed temperature reflects average molecular kinetic energy across states. Linking temperature, thermodynamic with kinetic energy, mechanical, bridged the disciplines. This molecular approach birthed kinetic theory, new physics frontier. This leads us to part three's focus. Recall Clausius's gas pressure molecular energy equation, but this formula requires a critical assumption. Regardless of initial conditions, gas molecules eventually reach uniform distribution through collisions. how to prove equal probability distribution across container space. And moreover, using probability to describe molecular states, Newtonian mechanics demands deterministic motion. Why probabilistic approach for molecules? This probabilistic model deeply troubled deterministic-minded physicists. Enter James Clerk Maxwell, electromagnetic fame aside, his kinetic theory contributions shine. Maxwell sought to decode molecular motion patterns at equilibrium, but with countless molecules and variables, how to calculate statistical approach, like analyzing class test scores through averages and distributions. Distribution charts reveal score concentrations. Maxwell applied this to molecular velocities. Maxwell's breakthrough. Molecular velocities follow normal distribution at equilibrium. Highest probability at median velocity, decreasing towards extremes. This became known as Maxwell-Boltzmann distribution. Why calculate this? The distribution enables total kinetic energy calculation, matching Clausius pressure formula. Maxwell achieved identical results through different methodology. Crucially, he bypassed Clausius's problematic assumption. Yet Maxwell's approach still didn't resolve the original question, proving gas molecules reach equilibrium regardless of initial conditions. Enter Boltzmann again. He expanded Maxwell's work with the Boltzmann equation. This equation describes molecular motion evolution over time, linking entropy with kinetic theory. Given sufficient time, molecular states approach Maxwell distribution. Entropy maximizes, but science thrives on skepticism. Critics noted, your derivation still relies on probability. Maxwell's distribution uses most probable speed. Isn't that probabilistic? This critique stung Boltzmann, but he refined his theory. Boltzmann proposed ergodic hypothesis as probabilistic reinterpretation. Under energy conservation, molecules eventually experience all possible states with varying durations. Maxwell's most probable became Boltzmann's longest duration at specific speed. This semantic shift proved ingeniously effective. Boltzmann relocated probability from molecular behavior to observer perspective. Imagine 10 rooms with a molecule moving between them. Frequent checks show most appearances in room 5. Not probability, but duration difference. The molecule visits all rooms, just stays longest in room 5. These theories laid statistical mechanics foundation. Ironically, despite Boltzmann's lifelong effort to eliminate probability from molecular theory, quantum mechanics later revealed inherent particle uncertainty. The 20th century ushered in quantum mechanics, physics's revolutionary new chapter. You might crave continuing this scientific saga, but tragically, Zhao Yang's life and book end abruptly here. Quantum mechanics and relativity, 20th century physics's twin pillars, deserve epic narration. Zhao's work focused on reconciling these theories' contradictions. His unique insights into both theories would have been invaluable. Sadly, we're deprived of Zhao's continuing guidance. For quantum or relativity insights, consider 7 brief physics lessons. Having journeyed through physics history, perhaps you now understand. What is physics? The answer emerges: discovering nature's laws through observation or experiment, expressed mathematically. The book concludes with Zhao's Science and Civilization lecture transcript. These public lectures inspired Zhao's book, delivered during TWM and Cold War era. Beyond historical review, Zhao offered wartime physicists reflections on science. Since 18th century, science's benefits drew praise. Yet Goethe critiqued Newtonian methodology. Goethe argued, lab-created conditions distort nature's true laws. He deemed this artificial approach sacrilegious. Public harbors primal fear towards scientific progress. Common wisdom says, knowledge is neutral. Morality lies in application. But Zhao argued, human curiosity inevitably leads to nature modification. Civilization's inherent drive. Once knowledge is acquired, we inevitably transform it into practical technology. Some technologies, like steam engines and electric lights, greatly benefit humanity. Others become destructive weapons, like atomic bombs. Civilization inherently actualizes all possibilities. Science provides these possibilities. As science progresses, humanity will inevitably discover more natural laws. Nuclear weapons were destined to emerge through this process. Zhao argued civilization must restructure alongside scientific progress to resolve existential contradictions. So, what is physics? This concludes our exploration. Find reading notes below the audio. Until next time.